Welcome to Grokking Graph Algorithms and Analytics. I want to cover a few more definitions so that we can keep developing a common language around graphs. The first thing I want to talk about is monopartite versus bipartite and k-partite graphs. The best way to motivate this is by discussing the technical definition first. So a bipartite graph, and I'm just going to quote the Wikipedia definition because it's actually a good way to contrast the working definition. A bipartite graph, or bigraph, is a graph whose nodes can be divided into two disjoint and independent sets U, V, such that every edge connects a vertex in U to one in V. So what that looks like is we have our set U over here, and we have V over here, and we have edges connecting like that. Well, they're not directed, so let's just connect them like this. What you'll notice with this definition is that there's no edges connecting anything in U. That doesn't exist. If that were the case, this graph would no longer be bipartite in the classic graph theory definition. Let's go ahead and contrast that with our working definition. A monopartite graph is a graph that consists of a single type of class of nodes. So what that looks like is, for example, a friendship network. So we have, Alice, and the only node we have is like a person, right? We'll say Alice knows Bob, and they both know Charlie. Contrasting that with a bipartite graph or a bigraph, we have two types of nodes. So we could have, for example, Alice knows Bob still, but they both work at, Cutco. So let's say knows and works at. So that's a bipartite graph because we have two types of nodes. We have a person class, and we also have a company class. And similarly, a k-partite graph is a graph with k different types of nodes. The difference between this definition and the more technical graph theory definition is that we allow connections between nodes in the same class. We just like to recognize the fact that we have multiple classes of nodes. The degree of a node in a graph is the number of edges incident to that node. For example, with this graph, we see that A has degree 0 since there's no nodes incident to it. B has degree 1. C has degree 1, 2, 3. What about node G? Let's see, we have 1, we have 2, we have 3, and we've got this edge, which is actually incident twice. So G has degree 5. Why don't you take a minute to see if you can figure out the degree of node E, F, and D. Okay, let's go ahead and look at node D. We can see it's got 1, 2. E has 1, 2, 3 edges incident to it, so it's got degree 3. And lastly, F has degree 2. Let's consider the following graph. One thing to note about this graph is that for any pair of nodes, They're likely to not be neighbors, but the neighbors of any given node are likely to be neighbors of each other. And, more importantly, most nodes can be reached from every other node by a small number of hops or steps. This is what's known as a small world network. Another way to describe them is to say they have a small mean path length, but high transitivity. Lastly, let's consider scale-free networks. A scale-free network is something where the degree distribution follows a power law. So what does that mean in practice? Well, let's think about it. We have a handful of nodes with very large numbers of edges coming out of them, but most of our nodes have very few edges coming out of them. That is to say, it looks something like this. We have the actual degree count here, and the number of nodes with that degree count, and a power law distribution looks something like that. What that looks like in practice is something like this. We have a few nodes with a lot of edges coming out of them, and most of our nodes have very few edges coming out of them. And this most accurately represents things like the World Wide Web, where we have a few hubs that handle a lot of data, and most hubs, they just don't have that many connections. There might be one here, we might spider out like that. But this is where that hub architecture comes from. Scale-free networks, scale-free graphs, are prone to attacks against hubs, but are relatively resilient otherwise. Let's keep going and talk about connected graphs. A connected graph is a graph where every member is reachable. That is, you can start from any particular node and follow a series of edges to get to any other node. This graph, for example, is connected. This graph now, if we add a node but don't add an edge, is not connected. You could also have what's known as a multigraph. To contrast that, we can look at a simple graph, which has just one edge between any given nodes, whereas a multigraph can have multiple edges between two nodes. So what that looks like is something like this. You see we have two edges between these two nodes and this third node as well, so this graph is a multigraph. Additionally, a graph could have self-loops. For example, if we have a very simple graph like this, if we add an edge here that has a loop, that's what's known as a self-loop. A complete graph is a graph where every node is connected to every other node. So we could have a trivial example like this, but if we were to add another node, we'd have to connect it to both of these, as well as to that. A weighted graph is a graph where all the nodes and edges could have a numerical value associated with them. So it could be something like this, where we have these three, and it's almost like the length between two nodes. So this could have length 1, this could have length 2, this could have length 2, and this could have length 5. And so it would be a lot shorter for us if we wanted to, for example, go from node A to node C. it'd be a lot shorter for us to go through node B rather than node D. A directed graph is a graph where the edges have a direction. So, for example, if we have this graph here, and we say that this particular edge can only go from node A to node B and not the other way around. And similarly, we have a directed edge from B to C and a directed edge from A to C. See that if we're trying to take a trip and we start at node C, there's no way for us to get out of there. We can't go along either of the two edges coming in to node C. A cyclic graph is a graph that contains a cycle. And what a cycle is, it's a path that starts and ends at the same node. So we could have something that looks like this. You'll see that we have a cycle with these four nodes. The last way to describe a graph is with sparse or dense, and that just refers to the number of edges that connect it. Lastly, I want to talk about trees. A tree is an undirected graph where any two nodes are connected by exactly one path. Another way to say this is they are connected acyclic undirected graphs. So that is, they are connected cyclic. So what that looks like would be something like this. We have a node. It has exactly one path there. And, we could go out that way and that way. So if you look at any particular node or any particular pair of nodes, you'll see there's exactly one path to get there. There's no cycles, and all the nodes are reachable. There's also the concept of a forest, which is just a collection of trees. That is to say, it's an undirected graph where any two vertices are connected by at most one path. So it could be, a tree here, and then we have another tree here. And they're basically just a collection of trees. Trees are a really powerful data structure. You can use them to build out search algorithms or autocomplete functions in typing and lots of other things. So it's really important to know and appreciate them. They're also a good way to develop some more complex algorithms because they sort of take out some complexity that gets built in with other graphs when you have things like disconnected or cyclic graphs. So we're going to use trees to help motivate some examples, and then we'll build out the algorithm and add the necessary complexity that comes in when you have more complex graphs. Well, we went through a lot of terminology, so I just want to review it very quickly. A few different ways to describe graphs are whether they're monopartite, bipartite, or k-partite. Okay, we covered a lot of things in this section, so let's go ahead and review them. There's different ways to describe graphs. We could say they are mono, bi, or k-partite. We can talk about their degree. And when we talk about their degree, we can consider small world or scale-free graphs, which have a particular degree distribution. We also covered a lot of different ways to describe graphs. For example, there's connected, there's multigraphs, there's complete, there's weighted, directed, and cyclic. So these are a lot of really useful definitions that we want to sort of remember and be familiar with when we're describing graphs and talking about graphs with other people. So if you need to, make sure you review this video a few times to get a better feel for these different graphs. There's also going to be exercises for identifying differently shaped graphs, so make sure you feel comfortable doing those as well. So that's the end for this section. We've discussed a lot of different ways to discuss the terminology around graphs. In the next section, we're going to start talking about paths, and that includes algorithms such as breadth first and depth first search, as well as some more efficient implementations of those algorithms and practical applications around those algorithms. Yeah, I hope you've gained a lot of good terminology in this section, and I will see you in the next section.